The first aspect of testing two different populations is comparing their mean values. So if you remember, mean value describes the location of our distribution in the sample space. So if we have two distributions with mean values mu A and mu B, then testing for equality of mean values is basically checking whether these two distributions could actually be assumed to be located around the same place. So testing like this would be equivalent to testing whether mu A minus mu B statistically can be assumed to be equal 0 or not. And comparisons of population means are common in assessment of medical treatments. So it can be either of the two cases. We may have a set of patients who are not being treated at all and another set of patients being introduced to a treatment, or we may have an old treatment, so patients who have results undergoing the old treatment, and then we try to introduce new treatment and verify is that new one better than the old one. So in both of these two cases, the first group, so either the no treatment in the first case or old treatment in the second case, are called control groups. So they provide standard, they provide a reference point to which the other group is being compared. And hypothesis testing in comparing two population means can be expressed in different ways depending on the type of the problem that we are having. So we may have two-sided hypothesis tests or one-sided ones. For the two-sided cases, we are usually testing for equality. So that means we would either test are the two population means actually equal, or is the difference between these two equal to a specific value, so usually denoted as delta. And that means that each of these is tested versus the non-equality, so of mu A not being equal mu B or mu A minus mu B not being equal delta. And now how we formulate this, usually we, as the null hypothesis, we give the kind of pessimistic case, which in this case would, for instance, mean that the new treatment equals, or the results of new treatment equal the results of old treatment, meaning that there is no improvement. But the alternative hypothesis says that we are looking for evidence that this null is not true, so that we have enough evidence to reject, for instance, the fact that the new treatment is not any better. In the second case, it's the same, but we are looking for specific magnitude of improvement, for instance. So we would say that the new treatment is better by specific value. In the one-sided cases, we are looking for explicit comparison whether something is greater than the other one or smaller than the other one. So actually in here, if we think of two-sided case, you could actually be just verifying whether the new treatment brings no results to the patient when compared with the old treatment. And in here, you would actually be looking for improvement. So the null hypothesis again assumes pessimistic case that the new treatment provides results equal or worse than the original, versus that actually, yes, they are significantly larger or the score is significantly bigger than the old treatment. Or the other way, if improvement, for instance, means that maybe some infection level should be smaller than 4, so the null hypothesis would mean that the infection level is smaller or equal with the first treatment, rather than alternative hypothesis that actually the new treatment brings smaller values. And so when we talk about two-sample population testing, just to get familiar with the terms, we will always be assuming that we have one sample, maybe having n observations, denoted xi from population A, with sample mean x bar, so this denotes the sample mean value, and standard deviation, sample standard deviation SA. So whenever we use S for standard deviation, it means we talk about sample standard deviation and not some theoretical one. Theoretical will come with the notation sigma. And the second population, so if we have population B, have M observations taken out of it, denoted as YI. So the sample mean is Y bar and the sample standard deviation is SB. So then if we consider the difference between the mean values of two populations, which is for our case tested as the difference between the sample mean values, so then the standard error of that difference equals the square root of rescaled standard deviation. So each sample standard deviation is squared, so we actually turn it into variance. Then we divide it by the respective sample size, and then we take the square root of that. So this gives us standard error, the base form of it for two sample population testing.